Hello, I am Nasir Ahmad, Assistant Professor of Physics, Government First Grade College for Women, Chintamani. So I welcome you all to this video on BSc 5th Sem Paper 503 under the heading Astrophysics, Solid State Physics and Semiconductor Physics. Now the content of this video is about the density of states of free electrons with the derivation. So what are density of states? So there are a large number of allowed energy levels for electrons in solid materials. So a group of energy levels close to each other is called as energy band according to band theory of solids. Each energy band is spread over a few electron volt energy ranges. So if we consider 1 millimeter cube volume of a material, there will be more than 1,000 billion permitted energy levels in an energy range of a few electron volts. Because of this, the energy value appears to be virtually continuous over the band spread. To represent it technically, it is stated as density of states. So, density of states is defined as the number of allowed energy levels per unit energy range or interval in the band associated with material of unit volume. So the dependence of density of energy levels or states on the energy is denoted by G of E. A graph of G of E versus E is shown here in this slide. In an energy band, as the value of E changes, G of E also changes according to the graph. And we also should note that the density of states at energy E2 is more than the density of states at lower energy E1. So now to derive an expression for the density of states, let us consider an energy band spread in an energy interval between E1 and E2. So below E1 and above E2 there are energy gaps. So G of E represents the density of states at an energy E in the small range dE. So as dE is very small, it is assumed that the density of states is constant between energy E and E plus dE. The density of states in the range E and E plus dE is denoted by G of E dE. Now let us consider a sphere of radius n in space with quantum numbers nx, ny, nz such that n square is equal to nx square plus ny square plus nz square. So number of energy states within a sphere of radius n are 4 by 3 pi n cube. So number of energy states within a sphere of radius n due to 1 octant of the sphere is given by 1 by 8 times 4 by 3 pi n cube. Similarly, the number of energy states within a sphere of radius n plus dn is given by 1 by 8 times 4 by 3 pi n plus dn cube. Therefore, the number of energy states available in between sphere of radius n and radius n plus dn is given by G of E dE is equal to 1 by 8 times 4 by 3 pi n plus dn cube minus 4 by 3 pi n cube. Or expanding this, we get G of E dE is equal to 1 by 8 times 4 by 3 pi times n cube plus dn cube plus 3n square dn plus 3n dn square minus n square. Since dn square and dn cube are very small and can be neglected, we get G of E dE is equal to 1 by 8 times 4 by 3 pi into 3n square dn, or G of E dE is equal to pi n square dn by 2. Now we have to substitute the value of dn and the value of n. To find the value of n and dn, we use Schrodinger's wave equation. And according to Schrodinger's wave equation, the allowed energy level E for a particle or an electron is given by n square h square divided by 8m l square. So differentiating the above equation, we get dE is equal to h square by 8m l square times 2n dn, or n dn is equal to 8 ml square divided by 2h square dE, or n square from the above equation is given by 8m L square divided by h square into E. Therefore, n is equal to square root of 8m L square E by root of h square. Applying the values of n and dn in equation number 1, we get density of states G of E dE is equal to pi by 2 8 ml square E whole power half by h times 8m L square divided by 2h square dE, or density of states G of E in the energy range dE is equal to pi by 4 8 ml square whole power 3 by 2 divided by h square to the power 3 by 2 e power half dE, or G of E dE is equal to pi by 4 h cube 8m power 3 by 2 L cube e power half dE. Now L cube represents the volume of the solid. If we assume that the volume of the solid is equal to unity, then G of E dE is equal to pi by 4h cube 8m to the power 3 by 2 e power half dE. Now, since each state can accommodate 2 electrons according to Pauli's exclusion principle, we can write the density of states in the energy range dE is equal to 2 pi by h cube 8m whole power 3 by 2 e power half dE, or rearranging the terms, we get G of E dE is equal to 4 pi by h cube times 2m power 3 by 2 e power half dE. And from the above equation, we see that the density of states is directly proportional to square root of energy.